Okay, so welcome to today's lecture in neural networks and deep learning. We started on Tuesday to look into how can we make models smaller, and there we looked into how to make it use less parameters. Today we will go in a bit of a different direction, how we can make models smaller, and we'll look into what is called quantization. So the idea is that we are having a more efficient way to store our weights, or maybe the activations, so that in a given memory we can fit in more in there, and then get therefore like maybe larger models in the same memory. So what we'll do is we'll start with the motivation. Then we look into different like quantization data types. So how can we do the quantization? How should we do like map floating point number typically that we have into some other data type? We'll look a bit into how that then really is applied and what are their additional challenges that we have to address. Then we'll look at different strategies of how we should do the rounding. So I guess you know by now quantization is that you have to do some rounding, and how we can do this efficiently, and maybe have to look at two algorithms. And finally, we look at some implementations, look what are the trade-offs, what are example algorithms that you might want to use, and especially at the end, look there also at what is called Q-lorem. But let's start with some type of motivation. Why is there no picture anymore? Okay, it's only for the first two. I'm sorry. Okay, I'll check that later, but you had the picture from last time, hopefully, that we see that over time, images, the models get much, much bigger, and therefore it makes sense to think about how can we make these compact. And we're taking today their different view. We are not trying to make these models smaller in some way, but the idea is like, can we make a more efficient representation so that we can use the same type of model? And especially that is interesting in the view, if we think of it, that we're interested in, for example, applying the models in mobile phones or applying the models on robots, then we have to make these models small in order to like fit there. And one major limitation typically nowadays is there the memory. We have thought of, if you look very, very much back, at the beginning, we talked about, of course, how you can do inference and training on putting things not on one GPU, but several GPUs. And so there is the ability to have really large models also on several GPUs and address this problem. But of course, GPUs are expensive. So if you can like have the same model or nearly the same performance on a lot smaller model, this is of course very much liked, because this would make things a lot more efficient. And how that goes is like we'll think about quantization. What does it mean? So here are three different models. We have a T5 model, which is an encoder-decoder model. You see 11 billion parameters. And then we have two llama models here, one with 33 billion parameters and one with 650 billion. And now it depends on whether you're doing training or testing, but just depending on that, you'll need a different amount of memory. What would you have as an additional memory need in fine-tuning? Why is the numbers bigger? Gradients, yes, that's one big issue there, but there's even more. You see, it's not just a factor by 2 or so, but there's even more. Similar to gradients, I have to admit. We also have to optimize a state. So in order to optimize, if you think about Adam, we talked a bit about what you all have to store. You have to typically store second order derivatives and so on. So a lot more additional things. And that's why you see there's really huge larger models going from inference to fine-tuning. What you now see and why it should be interesting is what you can achieve with quantization. So if you think about what we're currently having in GPUs, typically if you work in a lab at the university, you might have GPUs with 22, maybe with 48 gigabytes of memory, but having bigger GPUs, I wouldn't be sure if you write your master thesis that you'll get a GPU which has more memory. So the question is, how can we deal with this? And you see here, yes, with quantization, we can achieve really like significant reduction. And that's like how typically you're nowadays doing it, that you'll not store the full weights in there, but quantized versions. And that's what we want to look. But here that should motivate you a bit that this is like really essential in order to like efficiently train these models on best even a single GPU. It's necessary that you do some type of quantization, and you're not storing the full model, but you're storing a quantized model of it, and then trying to process everything of this quantized model. So the main question is why are these models so big? And if you think about neural networks, what you mainly store is numbers. There's different numbers we talked about. There's, of course, the weights you have to store. There is the activations that you have to store. In training, it's also the optimizer states and the gradients. But this is everything that we have to store in there. So we have to think about how we are storing these numbers. Because if we want to reduce the memory, of course, the one idea is to use less numbers, which means typically less parameters. If you have less parameters, you not only have less parameters, you also have less activations, you have less gradients to store, and so on. So by that, you can make the model smaller, and that's what we looked into last time. We can make the model smaller by having less parameters, and then we can maybe fit larger models. With this type of knowledge distillation, it's also good to get better performance with smaller size models, but of course there are limits, and typically the student is not better than your teacher. So the question is, can we also do something else? And the other thing is like, how do we store the numbers? And that's what we want to look into now. So typically you have either 32-bit or 64-bit. So you need like 64 bits or 32 bits for a single number. But maybe that's not necessary. And we'll see that today. So we can also get more efficient if we are just using less numbers for that. So we'll see like very successful are approaches which even only like use 4-bit for numbers. So then you're going from 32 bits to 4-bit. So you're reducing your size of your model by 1/8. So 2 1/8, not by 1/8, but 2 1/8. So by a factor of 8. And that, of course, would be very helpful. And therefore, we'll look a bit into how that will work. We'll start with a bit of basics. I guess you all know that, but sometimes it's good to remember a bit, like how are numbers really stored and so on. And of course, like typically we'll see that floating point numbers are like floats are the most important. We have normally weights which have values with decimal, but of course there's like we'll see that for quantization we'll then typically end up with integers, and for integers they can be stored in different ways. So the most commonly things is either unsigned integer, a signed integer, or two complement representation, meaning if you have an unsigned integer, you just take the bits you have and they will be arranged like an n-bit array will be able to represent all numbers between 0 and 2 to the power of n minus 1, where, as you all know, like binary representation, you're just like assuming that this array of binary values is like a binary number, and that's why, for example, here you get the value of 49 because it's like the 1 is here, there is the 16 and 32, and if you sum all of them up, it's 49. Of course, it has a bit of the disadvantage that you'll end up with only positive numbers. That's why there's two ways of represent positive and negative numbers. Maybe the most easy, straightforward way is to use a sign bit. So you have can only represent the numbers from -2 to the power of n minus 1 minus 1 to the positive value. And you just say the highest bit is indicating whether this is a positive or a negative number. If you're remembering back, maybe it's a long time ago, about like how numbers are represented. There's the disadvantage here that you'll have two zeros. So you can represent the 0 as a 1 with a minus before and without, which is maybe not the best. And that's why there's also the idea of the two complement, which can then represent the numbers from -2 to the power of n minus 1 to 2 to the power of n minus 1 minus 1. And there the minus sign just goes in that you say the first digit is not 2 to the power of 7, but 2 to the power of -2 to the power of 7. So if you have negative numbers, you have to put the 1 here. And if you have positive numbers, here's a 0. And so you mainly shift the upper scale to halfway to the negative. And this is how we are typically encoding integers. So when we are now quantizing, we typically store just integers. We're then learning a mapping, but that means if we have a 4-bit quantization, we can store mainly 16 different values in there with which we can calculate. Especially if we're working with neural networks, we don't want to only have integers, but we also want to have decimal numbers. There's different ways of doing that. This is maybe the more straightforward way, but not the way how it's typically done. So there's fixed point numbers where you have, for example, here the 2 complements, so -1 again. Then you have the numbers above 1, and then you're starting here with 2 to the power of -1, 2 to the power of -2, and so on. And then you can represent also like decimal numbers where you just specify hard, there's a decimal point. So there you go from 2 to the power of 0 to 2 to the power of -1. And so you have exactly the same numbers, but this is how the way you can separate them. It comes with a disadvantage that you have like equal scale, but it might not be like the best way to do. For example, for very small numbers, it would be nicer to have a more fine-grained representation. And for larger numbers, it's maybe not so important whether it's 5,000,000.73666 or 665. But for 0.73, that's very important. And then we're coming to the other numbers, which are like floating point numbers. That's a typical thing how you're working in neural networks, where you have your sign and you have your 8-bit exponent, for example, and then 32-bit for the fraction. And then in order to get that, what you're doing is you're saying -1 times the sign, 1 plus your fraction, so what you have here as a number below 1, and then times 2 to the exponent. And so here the exponent will be -2, the fraction is 0.625, and then the final number is this one here. So these are the typical ways of how we represent. So we also know, or we already see, like, yeah, even if we don't do quantization, there's a bit of quantization always in PCs because they're not continuous. We have to do a digital representation. But the question is, does it really need to be that fine-grained? Is it really important whether it's 265625 or 2625 or even more broad? And that we will try to optimize now. So the idea is, yeah, maybe we need not that detailed representation, but if we're doing it right, we can do less details and therefore store information in a lot coarser representation. In general, there are already large amounts of different type of floating point numbers. So here you see some typically used for neural networks, from the NVIDIA TensorFloat to half precision, full precision, and so on. And you see a bit, yeah, they are differing on the one end, of course, in how many bits they're using in total, but then also like how many bits are associated with the exponent and how many bits are associated with a fraction. So how big your numbers can get and how detailed they are in each one. So this is from what we'll start. And now the question for today is, how can we make these things in some way more efficient so that they are where we need less, but can be hopefully as expressive as possible. So you always see, of course, you can go a bit down by like shrinking your size. You can have less detailed numbers, but the question is, where do you need it? And what we are today focusing on is the case of inference. So when we train the model, when we're not, sorry, wrong. When we're not training, when we're doing inference. When training, things are typically more complicated. If you're training, I mean, you have to do your gradient updates and so on. And if you do too large quantization, things get very unstable. So today's focus will be during inference. The idea is maybe we need more details during training, but then in inference, we can have a smaller model. And the idea of quantization is, yeah, we're not storing everything, but we are constraining the continuous or a very large set to a small discrete set. And I guess you know quantization from a lot of things. You can do it from an image that you're doing like less detailed things. You can use it from a signal. You've done any type of signal processing. I mean, you can't store the continuous signal there, so you normally do quantization, and then you're getting here the error. You see, you don't store the exact number, but you're storing something in between, and you're approximating your signal by that. So that's the general. I mean, quantization has been done in a lot of various fields, but what we are today interesting is, of course, doing it for machine learning. So what does it do for machine learning? So the idea is we have all our numbers. For example, it can be that our weights are somehow between -3 and 3. And then we're not storing the exact numbers anymore, but we are only storing somehow which bucket they are in. So you're not storing exactly, but you're quantizing it and saying all the numbers within this bucket, they are the same, and we're storing them all the same. And then, for example, we can go from a 32-bit value into a 4 or 8-bit value, and only storing like 16 possible values of there. So meaning that, yeah, we slice our distribution into 16 bins for 4-bit, and then we are just storing in which bin they are. Then you cannot distinguish anymore this number from this number, but maybe that's also not too important. So maybe this is enough for storing. So this is, yeah, the main idea here. We're not storing all the details of our curve, of all the values, but we're quantizing the values and do not distinguish whether they are like where they are within the bin. If we want to do that, we have to do, yeah, several types of decision and in order to build the quantization algorithm. And the first one is like, what type of data type do we want to have? So what type of mapping we want to have from the in values to the floating values and back. So if we're saying, for example, here we have a 4-bit representation. So here we assume, yeah, they should be all the same size. That is a valid choice, that we say everything should have the same width. And so we have this type of error, but that's of course not the only choice. It might be that you say, oh, the most values are here somewhere between 0. So maybe we should have a more fine-grained solution here and a more wider spread solution there. So there is, and we'll see there's different ways of how you can come up with this type of mapping from the 4-bit to the full. And of course, you should have a bidirectional mapping, of course, adding some type of error. The second question we have to address is, how do we want to apply this type of quantization? So one question in the neural network is, of course, what do you want to quantize? Do you quantize everything? Do you, for example, only quantize the weights and keep the activations full? And then you always have to recalculate. Do you do the gradients also in training? And then also, like, when you now learn this type of mapping of quantization, do you like learn the same mapping for everything, for the whole network? Or you're trying to optimize, so you only learn a mapping for some part and then another mapping for another part, which of course means typically you have to save some meta information for each of the mappings. So if you're mapping only very few numbers, your gains might not be high enough. But therefore, it might be that some numbers are in a complete different scale. And then, of course, it would be helpful to know like which scale you're interested in. Finally, we'll look a bit into rounding. So when you now do the quantization, I mean, the obvious thing, for example, is that if we have this, then yeah, if you're between here and here, you will round to this one. And if you're here to here, you'll round to this one. And that is the default thing, but it might not always be best. So if your numbers by chance are always like at the beginning here, you always have a very high quantization error, and then at some point it might be good to like go to the other one. So if you want to optimize it not individually for each value itself, but more globally, then it might be to you try to optimize the overall performance and try to adapt that. So that you're not just round always to the next, but you also consider what are the rounding errors at the other point, at other values, so that in general, overall, you have the minimal rounding error. Finally, there's a question of how to integrate things. The basic thing is, okay, we're training the model, and then we're quantizing that, and then we're applying it. It's what people call post-training quantization. So you apply the quantization algorithm after you have done your full training, after everything is done. But that, of course, might not be optimal. During training, you just train to have the optimal performance, but you haven't thought about that you later apply quantization. So maybe it's better to already consider that during training, so that, for example, you train weights in a way that they are very, like that the quantization error later is minimal. And therefore, people also looked into quantization-aware training, where they use or like apply some type of quantization during training, or at least they measure the quantization error during training, but in order then to train a way that you can later optimize for that. Do you see any challenge on this one? Why this training could be difficult? Yes.
I think it depends on whether you use quantization directly as training or if you use it as an additional loss term. If you use it as an additional loss term, you will have more computation, but you will still be able to train your network with the higher precision weights. If you use lower precision weights, you might lose some fine granularity that you need to make important inferences that you couldn't have made without some intermediate steps.
Yeah, so that's one point. So things get more unstable normally during quantization. But even if you're only using it as some type of loss or somehow integrating it, and you're still doing the training on the full numbers, there might be one challenge about having either quantization as a loss or llama integrated during your decoding. There's one property of quantization which is not very good fitting to the training.
It's not sure.
Exactly. So it's typically not differentiable. You do hard choices. I mean, if you do quantize, you see very nicely, if you're here or here, it makes a big difference on your input. On the red one, it doesn't really matter. Here, if you're here and now change it to here, you have a small change on your input, but a large change on your output. And that is like difficult and not good to learn. And I mean, there are some techniques through it called straight through estimation. But in general, that's a major issue when doing quantized aware training. Good. Any questions to this type of general part about the quantization? Yes?
If you had a model that for a certain layer needed specific areas, let's say, for example, there are a very low number of requests around 0, but a very high number of requests around 1 and -1. You need the granularity at 2 points. How would you deal with that?
We'll see. So there is different ways. So I mean, the first one we're doing a bit like is k-means quantization, where that I think should work. But I have to say that typically it's like with people later look what linear quantization, and then it doesn't work. So we'll come to that a bit. And then I guess you have to think a bit about what I mean. For example, we'll see that I said already that you're not always using the same quantization for all numbers. So you can have like, if that's like part of your weights, you can like quantize the ones independently of the minus ones or something like that. So we'll see like blockwise quantization, and also like which takes into account how important some weights is and does different types of quantization there. So I hope we'll give some ideas during the lecture of how to address that. Otherwise, come later and check. So yeah, one idea is like k-means quantization, where the idea is we're not having like a direct mapping function, but we're doing some type of clustering. We're saying, okay, which are the most areas that are important? If we heard it, it would be like if you have mainly numbers around 0, 1, and -1, and you want to have 3 classes, so it might be good to make these 3 classes so you have a major idea of it. And so this is k-means clustering, what means that if you have your set of weights at the beginning, and then you're doing clustering, and you find your main clusters. And for example, you could here find the clusters 2, -1.50, and -1. So this would be some of the main clusters where you had covered some or most of this here. So what you then, of course, have to save is like you have to have this centroid, which stays you like for each of the classes that I have. So in this case, 4, that you store which are the main things. When you now cluster, the clustering is now quite straightforward, that instead of storing the original weights here, you mainly store the indices. So you have here your full matrix, 32-bit floats, very detailed. Now you have your centroid, you're looking into which class one goes. So on the top left, it's 2.09, that's nearest to 2, so you store your 3 here. And then we have the -0.98, it's nearest to -1, you store your 0 here. So what you now have done, need to do is now instead of storing this type of matrix, you're storing the index here. So for each bit, like for each number that you're interested in, what is the centroid, and then for your matrix, you only have to store your indexes. So the question, hopefully you have to store even more. So we store one matrix, now we have to store both our centroids and our indices. So the first question is this more efficient? Do we need to store less in this one than we had before? And let's do the math for that. So what we have to store is like we have 32 bits. So for each of these numbers, we're 32 bits. There are 16 numbers in here, which makes 212 bits or 64 bytes. What we also have to store is now the index, which is 32 bits times 4 here. So 128 bits, so 60 bytes. And this one is now, of course, more efficient. We have 4 possible values. So that's like 2 bits. So you have 2 bit times 16, the 32 bits is 4 bytes. So now we went down from 64 bytes to 20 bytes. So like a factor of more than 2, which you reduced, more than 3 even, to be honest. So you reduced to roughly like 1/3 of your space. Of course, you see already on what it depends. One important thing is how many numbers you quantize. The more numbers you quantize, the more efficient you will get. So every number you save now, instead of 32 bits, you only need 2 bits. So a factor of 16. While you have the additional overheads, depending on like how many classes you have to store. And of course, now if you're trying to store more and more numbers, things will get more efficient. Of course, kind of at a cost. That might also mean that you have more different types of values here. So your centroid approximation is typically getting also like significantly worse. And then what you can look at is you can also like reconstruct. So if you reconstruct the thing, is you take your index against create your centroid and get the numbers, and then up there you see like how big your arrows are, It's of course like depending on how central the numbers are to your individual things, and you see that some are better and some are worse there. What you then typically do is you store your things based on the quantized values, but you would normally do calculation, then not in this representation, but in this. So every time you do a calculation, you have to do it there and then store again things back. Still, often this might even be faster. Any idea why it could be faster and then like just storing these numbers and calculating, storing these numbers, reconstructing them and calculating again? Sounds maybe first a bit surprising why like calculating with quantized things, even if you do reconstruct things, this could be more efficient.
I think it's more memory efficient, especially in the GPU.
Exactly. So if your main limiting factor is the memory throughput between GPU and the memory, then you're more efficiently loading things here. So you can just load so much more. And if the calculation is not the main bottleneck, but the loading, then you can even be faster by doing that. So finding out what is fast is not super easy, and you really have to have quite a good understanding of both the GPU and your algorithm. Good. So that is one idea. And the other thing you can do is, of course, linear quantization. So how does linear quantization work? We again have our weights, and then we have to store two possible weights. The one is the 0 point, so the shift, and we'll even only do it sometimes. And then you have your scale, which says how things are scaled. And then you have your quantized values. So typically that's now you have binary, so you can do the binary to decimal. And now what you're doing is like, instead of storing 2.09, we store there 1. We normalize that to the 0 point, multiply by our scale, and then we get here 2.14. And here we get 1.07 and so on. So the formula is that things get mapped to their quantized value minus the 0 point times the scale, and that will give you here the overall. So you see here again the quantized error. So you see there are still errors. Now the main difference is before we had not equal distance between them. So remember we had the centroid 0, 1. I should remember we had 0, -1, and 1.5 and 2. So the distance is not all the same. So these two are nearer to each other than that one. This is, of course, if it's linear scale is no longer possible, they all have equal distance. All your 4 values here, if you look onto what they are mapped, they'll be, so you see that the one gets mapped to 2.12, the lower one is 1.07. So you see all of them have a distance of 1.07. So it's between 0, 1.07, minus 1.07 and 2.14. So the distance between all the points are equal, and it's mainly influenced by the scale. However, there's one big advantage by that. Does anybody see already what could be a big advantage?
You don't need to store the entire mapping between the integers and the centroids.
Exactly. So we only have to store 2 numbers. In reality, we'll even see we mostly even store only 1 number, because we assume this one is 0. So the scale, if everything is always around the center, so around 0, then it's good to just keep it. And then the only thing you have to store is 1 scale instead of n possible scales. So the linear quantization works in mapping R to the quantized value minus Z times S. So the important things you have to remember is the original number, the quantized integer, then you have 2 parameters. That is controlling whether you want to have your quantized values centered around 0 or like shifted, and the scale is then how much your scale things. Yes.
You explain again how you got to the quantized weights on the slide before. Like how did you get from 2.09 to 1?
Okay. I mean, you're again searching for the nearest value here, so you have to do rounding. So this is again what you see here is the formula you'll have seen here. So the right side is the quantized minus Z plus S. And if you now want to get the quantized, you can reformulate that. So the quantized is R divided by S minus Z. And then you have to, of course, do the rounding, because you see, I mean, if you do that, you'll get from 1 to 2.14. But if you round this one to the possible values that we have, then this one is the nearest one. Yeah. Okay. Good. Yeah, we'll come a bit more to this detail. So what is important in order to do this type of scaling and calculation is, on the one end, you have to know what is your minimum and maximum value of your quantized values. So if you have, for example, 2-bit, that's typically -2 and 1. If you have a 4-bit, it's -8 and 7, or in generally -2 minus n and 2n minus 1 minus 1. And the other thing is, of course, what are your minimal and maximal values that you want to represent? So you see already, in order to quantize, it's really like important to maybe not quantize all possible values, but if you want to have a good like scaling, it's good to have as small range as possible here, because then you can get more fine-grained. Because what you mainly do is these possible numbers on your quantized will be linear mapped to that based on R min and R max. And then you can also map 0 to 0 if you want to have a shift in there. And these are not equally between 0 and 1. And based with this knowledge, you can easily determine now the values of S and Z that we need. So first S, you see that the maximum value of the original numbers should be mapped to the maximum number of your quantized values. The same thing, the minimal value should be assigned to the minimal quantized. So if you like, I mean, of course, it makes only sense. The minimal value is exactly going there, and the maximum value is exactly going there. If you do these two, you can do the difference, then you can reformulate, and then you get S is R max minus R min divided by Q max minus Q min. Hopefully Q max minus Q min is not 0, because you have some range. Otherwise, of course, it doesn't make sense. But this way you can calculate then S. So if you, for example, from the example, if you have values between 2.12 and -1.08 in the matrix we had before, then you get exactly your scale of 1.07 here. So you have optimized your scale for this. And then you can also do your Z. So the Z should be an integer number rounded directly. So you put your Z in there, and then to get it's like -1. So you're doing a bit of a shift. As I said, often you even have values which are like somehow located around the R, and then you can save even this type of amount, because you're not you don't need to extra save that. Okay, so with this one, you can then also do like what you typically will do is like, if you want to do some calculation, so you have originally y equals w times x, so that's a typically multiplication that we're doing, where when you're doing that in quantized, so then you have the s of y, q of y, and z of y. You see, you're not assuming that your scale is always the same, so you typically have different scales for different parts of your network. And then you can put here your w and your x. And if you want to calculate directly your new value, you can do it this way to do the calculation. What you can simplify is that we often assume that our weights have some type of normal distribution. The nice thing is, when you have the normal distribution, you have it centered around 0, meaning that you don't need to have that x. So the last twos get 0, and what you then only have to do is like the S is just R max divided by Q max. So you just said that z is 0, so making things a bit easier. So you're not allowing here for the shift, but just 0 is always mapped to 0 in there. And then this calculation gets also a bit easier. Good. Any more questions about the linear thing? There is a bit of, yeah, one type of disadvantage is that we have somewhat equal size for all our bins. So that's like the typical thing of linear. Like if we want to linear, of course, each bin has the same size. Which without any prior knowledge might be good, but in some application that might not be super helpful. If you're having like the one bit where there's very few and others there's a lot of values, maybe these differences are more important, and maybe therefore you want to somehow do a different type of quantization. And therefore there are some other quantization. So for example, what is called the quantile estimation, where the idea is, okay, we want to have somehow equal number of elements in each bin. We want to do that. We of course need to estimate what is the distribution. What would you take if you have to assume a distribution of your numbers? What would be a good estimate? Any suggestion? I think I heard it already. I mean, normal distribution is typically good. So you can assume your weights are somewhat normal distributed, and then you can try to make based on the normal distribution, store your floats so that you, again, of course, quantize 0 to 0. You rescale the values between -1 and 1, and then you have bins based on the normal distribution and not equal bins here directly. That is also, we'll see this, that is what is called the normal float, and that has been also used for some quantization algorithms. Yes?
How well does the setup is actually hold up in
I don't know. I have to admit, I wouldn't be surprised if it holds up, especially for weight. I mean, it's not for any numbers, so we'll see. So typically, you're quantizing your weights of the model. So for any number, I'm quite sure it's not. There's like typically in human right numbers, I think 9s are a lot more common. So there is like not a nice thing. But if you think about weights, I wouldn't be surprised if it's the case, but I can't guarantee you that it's really the case. Yes?
If we do like a 2 regularization, then we kind of enforce that, like with a loss term.
To be about 0, yes. I mean, yeah, you're enforced to be near to 0. Is that really enforces this time? I could imagine, but I wouldn't be sure that I can prove that at the moment, I have to admit. But at least it's a good, yeah, I see the point that this could enforce it. There is one last different way of doing this type of data type, and that's what's called the dynamic exponent quantization. We'll only have it very briefly. The idea is that we want to have a bit of like a high precision for small and large magnitude numbers, and for the intermediate not. And the idea here is that we no longer have like fixed lengths of your exponent, but you can have different ways of your exponent. So what you have is you have first a sign bit, then you have here bits for the exponent, then you have an indicator bit which says now the exponent is over, and then you have here the fraction like the floating point. Of course, it maybe is in some way inefficient that the exponent is like stored just the length of this exponent, so you can't have large numbers. but it's also like one. I mean, the nice thing is then you can have very large numbers with a large exponent, and if you have small numbers, you can have more details on the floating point and put more. Because the representation of your exponent by just the number of zeros is very inefficient, and you can't do that many there. But yeah, in that way it's very different. So we're not trying to store these things somewhere else, but we're storing like things differently in a directly in a float value. So you're not mapping back to integers and storing them, but you're just trying to have a more efficient representation of your floating point numbers. Yes?
Is the sign for the exponent or for the fraction?
I think it's for the fraction, yes.
So then you can only have exponents in one direction, right?
Yes, I would assume so, because otherwise we couldn't have the good point. I didn't think of it, but we couldn't have the minus. Otherwise we can't have minus values if this is not the case. But yeah, so you can only have them in one direction. But again, it's the idea if you have weights, you typically have them between -1 and 2. So it's like especially interesting for Newton. But a good point, yes. Good. Any more questions to data types? Good. Then let's see if everything has been solved. And I guess lecture is not over, so not everything has been solved. So what can typically happen is we might have this type of outliers, and that might make our quantization very, very ineffective. So if you, for example, most of your values are between -3 and 4, but there's one value which is 10. What that means now is, yes, your linear quantization has to quantize all values between -10 and 4. But except for one number, you're only using the ones between -3 and 4. So in reality, you're not really having a 4-bit quantization, but you're mainly only using these 3 bits there, so half of your numbers. The other half, the 4th bit, which gives you the other half, is not used at all. And that, of course, is somehow not really very, very helpful, because, I mean, you want to be as precise here. So you could be double as precise here if not this one outlier would be there. And that typically happens, like if you especially store different types of numbers, that can happen if they're not all the same and so on. So any idea how we can address this? It's maybe a bit far-fetched, I think, but maybe you have some ideas. If you have this type of outlier, how could we address it? Yes?
K-means would organically.
Yes, if we would do k-means, we could address this. The challenge is then we always have to store like all the k values in there and not just one single number. So the nice thing about the linear quantization is that we only have to store like one number and not 2 to the power of n numbers.
Then for the outliers, we could just add some flags which have some or more of the numbers, but most of the numbers will still be represented by the one number.
Yes, that's good. We'll do something similar in between. There's one catch with that. That's like a bit mixed precision calculation. That's typically not super fast, but it's a good way. The surprising thing is not too much, a lot less thought about, but if the quantization error is there, maybe it's good if the quantization or like this inefficient quantization is valid for all our numbers, but only like a small fraction of the numbers. So the idea is, okay, we're not using the one quantization, linear quantization for all our numbers, even not for all our weights, but we're splitting our things into a decent number. So for example, into blocks of 64 or something like that. And that means if we have now 1,200 like numbers that we want to store, then we're storing them in 16 blocks. And for each block, we store the scaling factor. So you're no longer like quantizing all your numbers together, but you're mainly splitting all your numbers into 64 bins and or like consecutive numbers just, and each one is quantized. Why is that helpful? Yes, we have still the problem with a bad quantization for the first block where the outlier is in. So there you see still this on the left here. I know it's a bit hard, but here, I mean, just from the distribution, you see that not all numbers are used. It's still here 10, so you have still the inefficient representation. But only for the first 64 numbers. All the other numbers here, you see a very nice distribution. It goes roughly from I think minus 5 to 4, but like all values are covered. So the quantization error for all the others isn't as big. So you do your quantization since you're not using the same like scaling factor for all, but for every 64 numbers you're using a new scaling factor. Since the scaling factor is the main one which makes things inefficient because most numbers don't occur, this inefficient one now only addresses the 64, and all the others are no longer really addressed by that. Yes.
What all the choose the blocks in. So can you dynamically assign? Do you have a special mapping that you can say this way and this way and that way for this block, or do you just take the first 64 numbers and say they go in the first block?
Do you have an intuition or somebody else? What would you do? Would you like assign every word to one of the 16 blocks, or would you do just the first 64? Yes?
To store as little information as possible, so we would just use those first 64.
Exactly. So if you would do like, I mean, of course, you would be more efficient if you would like do like for every, not efficient element. You would have less quantization error if you for each number would find the optimal block and put it in there. But as you say, then we have to store for each number the block ID, which is again, if it's 16 blocks, it's 4-bit. So we are doubling, if we're going to 4-bit quantization, we're doubling our quantization. So that seems to not be super efficient. And that's why you typically just do consecutive blocks and then store just for each block the one number, because then it's like implicitly stored and you don't have to store this information as extra. But a very good point. So that makes things of this quantization really like difficult. You always have to store like what should you store. So every extra information, as you said, if you store them, might make your quantization less effective. So what does that now mean for the block-wise quantization? So do a bit of calculation. So how costly is it that we're doing block-wise quantization and not everything? So just assume we're going from a 16-bit quantization to a 4-bit quantization. The block size is 64, not 64-bit, sorry. We're having a linear quantization, so we have to do like one scaling factor. And we're doing that, the 0 is really like mostly it's working, so we're only storing the one scaling factor, which we store in 32-bit. That means we have one 32-bit value per 64 parameters. That means that we have 0.5 bits in average for each parameter additionally. So even if we do 4-bit quantization, in memory it's not 4-bit quantization, but 4.5-bit quantization, because we have to store these quantized values and additionally always our scaling factor for them. And when we would, of course, store our whole model with one scaling factor, that would be more efficient. If you have millions of parameters, it's like very small, though you don't have to do them. So can you do any better? Do you have an idea? Can we go down from 4 to 5 to something more around 4? Any idea? Yes?
You could use compression.
Yes, but don't get too, I mean, compression, you have to decompress calculations again. So yes, you can do that. I would assume it's not done because things get too slow, but maybe I'm wrong, and so I wouldn't be even sure about that. There's an easier solution. Do we have to represent this one as 32-bit, or do you have an idea what we could do there? Our scaling factor.
Quantized scaling factor.
Exactly. So we just do what is called double quantization. So you first quantize with your value, and then you quantize this one again. So now you quantize your scaling factors. And of course, these ones we don't have to now, like we can do, for example, that is done in this one QLOR. So for 256 blocks, you're storing now the 32-bit float again, but for each block, you're only storing in 8-bit. So you're not going as much down because the scaling factors might to be wider. What does it now mean? So when that means instead of what we have in addition to our 4-bit is now we have on the one hand 8-bit for each of 64 parameters. So for each block, we have to store our 8-bit quantized scaling factor. So 8 divided by 64 bits. And then we have to store the meta scaling factor, so the scaling factor of the scaling factors. And there we have one 32-bit number for each 265 blocks, which each has 64 parameters. So it's 32-bit divided by 64 times 256 parameters. And then we are going down to in total of 0.127 bits. So you have now really like just a bit more than 4. So instead of 4.5, you have 4.127 parameters in there. So you're seeing things get really like you're trying to optimize. But yeah, that is one way of how you can like make these things even smaller. And that's, for example, we see that later, like one of the most commonly used quantization thing is QLoRa. So you can like train a model where with adapters, if you remember, so you quantize your main model and then you train the adapters normally, and there this is used. Good. So this is a bit on the application, and then before we're looking at several examples, let's go into a bit of rounding. Before we are doing that, do you have any more questions? Good. So how do we now assign like the quantized value for the to the quantized value? So we said in linear quantization, R is Q minus Z divided by S, or Q to get the quantized value, we take the original value divided by S and plus Z. So this is how the straightforward way, I guess you all would do it. You would take your original value, you divide it by S plus Z, and then you get your rounded value. So if you do that, then your rounding error is the different, the rounded number you get back is this one packed together. And so the error you do between these two is round 0, then plus and minus that. There's even no rounding in that. So mostly it's mainly, this is your rounding error. So the rounding error is like the rounding error of the round of the original divided by S divided times S. So how big your rounding error is. So typically you will round to the nearest. So that's mostly what you're doing. And I guess all of you, if I ask you how to round 0.7, you will all round it to 1. I mean, that's like just a normal rounding. So if we're doing that, then the error is between 0.5 and 0. We're doing uniform distribution. Between them, then we have somehow an expected error of 0.25. Which means if we have this, so the rounding here, so the overall error is like 0.2 times S. Of course, if you have a larger scale, if you scale your values more, it's obvious that your error is also getting higher, because that's like how you quantize. So if you're, I mean, the rounding error is of your original number before scaling, if you now scale them larger, your rounding error will go bigger. And if you scale them smaller, your rounding error will get lower. So the question is that all you can do, or can we be even more efficient, or like minimize the impact of this type of rounding error? And to do that, so to somehow investigate where we can look at to minimize the effect of the rounding errors, there's two things which are currently very commonly used. The one is a variation of what is called the optimal brain quantization. What is the idea behind that? So when you're doing that, the rounding, you're individually rounding each element to be optimal individually. But of course, if we are now looking at, I mean, typically we will, so example, round the weights and then apply it to the input. And do you see anything that might happen then? If you individually round each value.
The errors would accumulate if you do matrix multiplication because you round first and then multiplication.
Yes, so you're oh no, that's too fast. Yeah, the rounding error might add up. So you have the rounding error at each time, and they might add up. It's of course not easy to we store the metrics, so we can't like first do the multiplication and then do the rounding, because we have stored the rounded values and then we only get the input, so we can't do that the other way around. But what we should consider is it really the best to round each element individually, or when we do the rounding, can we already consider what we are doing later with it, and then maybe if all of them get rounded one too low, it might be good to take the last one and round it one up. So if you have always 0.5, you always round up, maybe it's better that you're somehow accounting for that, and then some you round up and some you round down. Because then hopefully your overall error is a bit lower than, because you're not really interested in the individual error. So it's not important that the rounding, how big the rounding error for one specific weight are. What you're interested is that your final output is as similar as possible to that. If that is our case, maybe it's good to optimize for that. So that is the idea of optimal brain damage. So the idea is that we're trying to, not brain damage, brain quantization. So where I'm saying, no, brain damage is even not wrong, because that is a bit of motivation of this. So there is a pruning strategy, which tries to remove weights from a neural network, and they try to selectively remove them, and the name of this one was optimal brain damage. So there is a way of it coming from. So how does it go? So what we are needing then is, first we need a small set of optimization data sets, so some inputs. If we want to minimize the effect of of multiplying something to that, we need examples. So there can be random numbers, but even better real data. So we see what are the typical calculations, and we can somehow minimize these effects. What we then want to have is we want to find a quantization matrix WQ, where the difference between the product that we're doing for the non-quantized weights and that we're doing for the quantized weights is minimal. So how can we do that? And that, of course, is a bit of a complex optimization problem here. You want to have somehow the whole matrix in there. How should we find the whole matrix in there? So the first question, if you have very many numbers, is, can we simplify this type of test? And the nice thing is, yes, for matrix multiplication, we can simplify things. Not all parameters depend on all other parameters. Any idea which ones are independent of each other in that way, where the errors are independent of each other? So what you can do is, if you look at what you're doing is matrix times X, that means you're taking a row of W and multiplying it with X. You take the next row and multiplying it with X. And these are the individual numbers. So there's only like something happening between the elements in the same row. Like elements in different rows, they come to different types of output, and therefore they cannot influence each other. So it can only be within one row. If you multiply things, then you add up things, and so you could try to like account for that so that they are not all rounding the same arrow. But if something happens in the top line, it has no influence on what is happening in the lower line. Yes?
What if you consider downstream computation? So if you multiply the matrix after the first matrix, then the different rows of the first matrix will have an impact on the same row, the second matrix.
That is true, but we are only optimizing here the direct output to be minimal. And for this type of optimization, it's not. Of course, I mean, yeah, you can make things have more and more impact, but here you're directly only looking at the output of this type of calculation. And so what you can do is, instead of the argmin of the full matrix, you do the argmin of the sum over all rows, and then you always multiply the row with X and the quantized row with X, and you try to minimize this type of things. And now comes, oh, it's not damage, so it's surgery, I'm sorry. But I think there's both even. So it's motivated by an algorithm called optimal brain surgery. And so the idea is you quantize not all the same, but you always look at finding the weights with the smallest error. You first quantize that, and then you somehow adjust the other weights to it so that overall you get the overall thing. So the calculation for that is a bit more complicated. We're working with the Hessian matrix, but you should remember this idea that it might be best to not quantize each element independently, but look at the final output. And if you use weights to be multiplied by your input, it might be better to like look at the overall error and try to account for that in order then again to minimize your overall error. Good. Any questions to that? Good, then we'll get to AWQ, which is partly a rounding thing, partly a bit of a trick. I think it fits best in there. So what there's the observation is, if you have these large models, like large language models or so, it is not all weights are equally important. So some weights have a significant impact on your output, and other weights are not really that important. So that's one characteristic of a lot of large models, that they're heavily over-parameterized. So it's very important for some important weights how they are, but others are less important. And they did one experiment here is like, if you quantize everything, yeah, you see, and you round it always to the next, you get a perplexity of 43. So perplexity is a measure of language models. They do that in a language model, and the lower value is better. And you see, if you're just doing quantization from FP16 to IN3 here, I think even, then you're getting a bad performance. Now, what you can think is like, when the first idea is, oh, if you're only interested in if like only very few parameters are important, we can do what was mentioned already before, that we are not quantizing these weights. So we are quantizing all the unimportant ones, and then the important ones we're keeping. And they did this experiment. How we identify, we'll see soon, but when you quantize like 1%, so just 1% of all the parameters is kept originally, and your perplexity goes from 43 to 30. So it's a lot better. But just like 1% of your parameters, you don't quantize, but keep the full representation. So then, of course, the first question is, how can you find these important weights? Any idea? Yes?
Activation maps.
What do you mean with activation maps?
So essentially you look how large the absolute value of the weight of the input going through one weight is.
Exactly. So that is so there could be two questions. So the first, maybe more straightforward, is like you take the largest weights. So thinking this has the largest influence. They found out that doesn't work that good, but they identified that if you look at the activation, this really works. So what you look is like in average, if you apply these weights to the input, what is the resulting what is the resulting activations for that? So if you put something in, you multiply what is the result of that, and then you do that again over some training data or a sample data, and you're getting like which weights like result in the largest activations. And there they showed that like if you use 1% of that, then it's enough. And for the others, of course, they use the quantized versions. So that sounds first as a good idea. However, it comes a bit of a cost. No, I showed already. What we now have to do is like a bit mixed precision calculation. So sometimes you do FP16 for the important numbers, and you do quantized values for the other ones, which is in some way a lot less efficient. I hope you remember from GPUs, it's always good if you do always the same thing. Now we're not always doing the same thing. We have to sometimes do floating point operations, sometimes quantized. So the question is, can we also do something else? And the idea is, yes, we can. We're just quantizing values differently on their optimization. And how it's done differently is maybe a bit of surprising. So what we can do is we can reduce the quantization error by scaling them up with a bit of heuristics in there. So how does that work? So we said the error of the quantization is round of the original value divided by s times s. And so if we're now thinking of, we're taking the product of our quantized value times x minus the original value times x. So that is the error of the product that we, instead of using wx, we're using the quantized value times x. So by quantizing w, we're not really interested in how much effect that has on the weight itself. We're interested how much effect does it have on the result of the product. If you're doing that, that's wq minus w times x. And here the quantization error we said before is 0.5 times s times x. Then, of course, the higher your input is, the higher also your quantization error is. So what you can now do is, instead of quantizing w, you quantize w times t. So you have a scaling factor. We'll later see how you do your scaling factor. In order to have here still the right result, now you also have to apply your scaling factor to your input, and you have to divide it. Because if you here multiply with t, and here you divide by t, then hopefully you all agree that the product is still the same. So the only thing we're doing different is that we're quantizing a different value. So we are not quantizing w, but w times t, and then we have to also scale things here. If we now look at the scaling error, so that means if we reformulate, that's the difference between wt and quantized and non-quantized times x divided by t. Because in order to have the wt here, you have to also add t here. So the overall error, again, the quantization error is 0.5 times s, but now it's times x divided by t. So if you're now using t, your error is a lot smaller here. You see it's divided by t. So if we have here a factor which is higher than 1, then our error on average will be lower here by this factor than by the upper one here. which sounds nice. So we have some type of trick to reduce our error. Of course, we have to be very, very careful. It's not always the case, and that's why we can't do just, I mean, that would be easy. We just multiply by 5 million, and then we mainly have no quantization error anymore. So that's not completely true, because what we have assumed that our scaling factor here stays the same. What is a scaling factor? Remember, the scaling factor depends on the maximum value that we want to quantize. And we change the values that we quantize. Before we have a list of values, and now we are not quantizing W, but W times T. So if W was our highest value, now the highest value is T times, so we would have the same type of quantization error. So it only works if our weights here are not the highest one, but more in the middle one, so that the error is not. So what you're mainly doing here is this only works if you first of all don't scale too much that it's going out, and then you're not always hit like the largest value. Why? How does it fit to what we had before? What you mainly is you do quantize your values in this scale at equal buckets. What you do now is your important things, you move them from more the middle to more the outside. And on the outside, of course, relatively seen, like a quantization error is not as big. So whether you are if you have values between 0 and 10, or minus 10 and plus 10, if your values are around 1, 0.5 is quite big. If your values is more at 9, 0.5 is no longer as big. And that you're trying to do here, that you're somehow moving the important weights to the outside of your scale, because there the relative rounding error is smaller than inside. Any questions to that? Yes?
Is the axe quantized as well?
No, so typically, I mean, now it depends, but typically you only quantize your weights and you're not quantizing your inputs.
If you quantize it,
Yeah.
how do you do activation functions?
I mean, often if you quantize, you even do like the calculation with the kernel in the original thing again. So you're not calculating in your quantized representation, but you're calculating. But of course, otherwise that is a major challenge to do that. So the only question, if we want to do that, is like, how do we select T? And now we found a better T already. So the idea is that we are doing it based on our average activation. So you take your inputs here, you scale them based on your average activation. Then we have an additional scaling factor alpha, which says how much should we trust on that. That's the one thing you optimize, and then you're multiplying. So the idea is, as I said, so you want to have a bit the lower you try, if you want to distribute your quantization errors, you're trying to move the quantization errors to the elements which are not so important. And for the important ones, we have a bit of a less of an activation error. Good. Any questions? Yes.
We do not scale every weight values by T.
I mean, here you would even scale all of them again, because you're just taking this activation by alpha, but then it's like some you're scaling more and some you're scaling less, because then it's again no hard decision, but you're trying to like, the important one gets scaled more and the other ones, yeah, whether you're not doing it or only a bit, it's not so important.
But then we need an alpha for every weight.
No. The alpha is fixed. You have the individual weights here based on the activation that you have on this weights, to which activation do they lead on your sample example things. So this ones you once calculate and then you use them all over again. Good. Any more questions? Good. Then let's have a look at a bit of like what effect does it now all have, and maybe how these methods are combined in some typical example. So first, we can like what is like a bit good bit size you should use. Of course, it now depends on which algorithm you use. So this is only for one, but it gives you a bit of an hint, and especially like an interesting result. So what you can do is now you can take different model sizes. So typically, if you have models, you have different sizes, like 3 billion, 8 billion, or something like that. And each of the models you can now quantize with 3, 4, 8, and 16 bit, for example. Depending on what quantize you'll get a different total number of bits of this model. So for 4 bits, for example, here in orange or yellow, like this model with this size is then similar to maybe this 3-bit model with a lot smaller size. And then for the 8-bit, this is again higher, and so on. And then you can look, hey, for a given model size that they have, how do they get the best performance? Because that's mostly you're interested in. So what is the most efficient way if you have a given size? And there you have the trade-off then. Yeah, you can use a bigger model, which is normally better, but then you need more quantization, or you can take a smaller model and then you need less quantization. And here is like for like one model called OPT, they did the mean zero-shot accuracy about a lot of benchmarks. And what you see is, at least for these, the 4-bit is typically a very good trade-off. So if you want to use a model, a good way is to do 4-bit quantization and then use the largest model that somehow fits into your memory. If you're going to 3-bit, things get a bit unstable, and 8 and 16-bit are often also not as good. So if it's possible, you find a small enough model which fits into your memory with 4-bit, then this is typically a very, very successful way of doing it.
Do the total model bits in the graph correspond to the original total model bits, or?
No, after quantization. So otherwise it wouldn't be a fair comparison. So it might be that, for example, this and this model is the original model, is like the same type of model, just one's with 4-bit and one's with 3-bit. And you see there is no, this one is very slightly better, but not very much. So you see, okay, you're not losing significantly when going from 8-bit to 4-bit. Then you can look at also as a block size. So there the difference is not as high, but you see again, if you look at the total model bits, like the 64-bit seems to be very good. So using a block size of 64 to do your quantization again looks like a very decent approach to quantize your model. You can also look at different data types. And for example, the dynamic exponent, although it seems interesting, wasn't too successful. It was better to use either the quantiles or some type of float in there for this type of experiment. So you see, you have to do that, of course, experimental, like finding out what is the right way. If you now look for a quantized algorithm currently, for example, very successful ones are what is called the GPTQ, which is a post-training algorithm. So you apply that post-training, as we've seen all our algorithms to date. What it does is it does a linear quantization, and the weights are quantized in 4. The activation are float 16, and we do the dequantization on the fly. So you're then, for the calculation, you do that in a fused kernel, and as we mentioned before, that can even lead to faster calculation. That you do also here group-wise quantization, or like block-wise, as we have seen, and it's using an adapted version of the optimal brain quantization that we're discussing. So where you always try to find the more optimal rounding instead of always rounding to the next. The other one, which is commonly used, is AWQ, which is also post-training, which is using the rounding from AWQ, also integer 4 and float 16, and where you use this activation. So one important thing is, of course, for both of them, if you remember the rounding strategies, you need some small development set in order to adjust, to estimate what is the right rounding strategy, and that has to be done there. Good. And then the last one, which is very, very commonly used, is the so-called Q-LoRa, where people use a 4-bit normal float quantization of the baseline model, which double quantization, and it's even optimized for some type of paging, and is especially interesting for this Q-LoRa is then used for training. So the base model is quantized, and then you're trying to optimize that you can how you can do your adapters. So if you remember, that's typically the LoRa was these types of adapters. So that's a way of efficiently training your model or your adapters on them. And what is the efficiency? So if you fine tune a model with, for example, 60 FP16, that means the weights need 2 bytes, the gradients need 2 bytes, the optimizer states needs 8 bytes. So in total, you need for all your weights like 14 bytes. So that means you need something like 17 GPUs to train a large model on that for like 65B model. So the first thing now you can try to do is make things more efficient, is to train in a LoRa way. That means we're not training all parameters, but we are only training like adapters. It's not only more efficient, but it's also like we learned that there's more, you need less parameters and therefore less data. If you do normal LoRa training, what does it mean? Yes, you have still 16 bits for your weights, so that is the same, but you have a lot less parameters for your adapters. So the weights you're training is a lot less. So that compared to the original weights that you have, you roughly have 0.4 bits. So for each weight, 0.4 bit for an additional weight on the adapter. And then you have to store the double thing for the optimizer and for the gradient also. So we are going from 12 bytes per input weight to 17.6 bits. So instead of storing your weights, I mean the weights are still the same, but you have additional weights as your adapters, and only for them you have to store the optimizer state and the gradients. And now that already reduces significantly the number of parameters. So now we can go to 134 gigabytes. So instead of at that point 17 GPUs, you only need 4 GPUs to train your model. So a factor of 4. If we then go for Q-LoRa, we can store our weights instead of in 16-bit and 4-bit. Then of course we have to store our adapters as before. So that means we now only need 4.6 bits. So we only need 45 gigabytes of memory to train the model. So even this large model can be trained on at least a large GPU. So you see by combining things, for example, by training only part of the parameter, so you only have to store that, and by quantizing the values, you're then able to like train a really large model on somehow a decent hardware. Good. So this is all for today. I hope you got a first impression of how to do quantization, what to address, and how this affects your overall performance. Do you have any more questions? Good. Then thanks a lot, and see you again next week.
Yeah.